one of the things that inverses are very useful for is determining if functions, should I say compositions are useful for, is determining if functions are inverses. Okay, so we have this sort of tenet or this idea here that two functions are inverses if and only if their composition is equal to x. And what you want to think about, make it very basic to start. So like if I had f of x is equal to 2x and g of x is equal to x over 2. When we talk about inverses, we talk about undoing, right? All of the operations in one function have to be undone in the other, right? We have to see the inverse operations. So clearly from this, you can see this is 2 times x, right? So g of x, this second function here, has x divided by 2. So clearly we are doing the inverse operation here that we are over here. And if I do their composition f of g of x, okay, we end up with g of x going into f, right, when we do this composition. So we have x over 2 being substituted into that function, which becomes 2x over 2. The 2's cancel, we're left with x, okay? And 99 times out of 100, when we do the alternate composition, where we switch them, you're gonna, if you get an x here, like I said, 99 times out of 100, you're gonna get that same result, but we should check it anyway. So now we're taking f of x and we're putting f of x into g of x, right? So we're putting a 2x into the input for g. We end up with 2x over x, the 2's cancel, or excuse me, 2x over 2, the 2's cancel, and we end up with x. So we can make our statement here, therefore, that f of x and g of x are inverses, okay? And I'm going to slide into this next problem here, okay, where we see an example, something like this. Now, when we talk about inverse functions and the quote-unquote undoing of operations, when you look at this first glance, right, do the eyeball test, okay? Could g of x be the inverse of f of x? Well, what do we see here? We see multiplication in f of x and we see subtraction. What do we see here? We see addition and we see division, right? Addition is the inverse of subtraction and division is the inverse of multiplication. So we see those inverse operations. However, if you take a closer look, in order for g of x to be the inverse of f of x, there has to be a positive 4 somewhere over here. There has to be a plus 4 because there's a minus 4 here. So it's not just about the operations, it's about what we're doing with those operations, what numbers we're using, okay? So as we can check this, though, in composition to see, if I take g of x, if I take this function and I plug it into f of x, then all of the, in this, you know, the very technical term, all of the doings, all of the operations that are here should be undone by this, right? And that's what we would get if they were in fact inverses. So if I plug the g of x function here into f, okay, we see this 2 isn't going to cancel with this 4, right? This 2 maybe will reduce with this 4, okay, where I now have a 2 on the bottom, but this is x plus 2 over 2 minus 4 now, okay? And does it look like I'm getting x? Not necessarily, okay? If I want to combine these, if we want to take it one step further just to verify this exactly, if I want this to be over 2 so that I can subtract it, then I would have, because it's 4 over 1, I would have to multiply both the top and bottom by 2. So now I have x plus 2 over 2 minus 8 over 2, and we would end up with x minus 6 over 2. There's no way to get rid of these and be left with just the x, right? So this composition did not produce x as a final answer, therefore they are not inverses. Okay, so we use composition as a method for determining if functions are inverses by seeing the inverse operations undoing all of the operations to x.